Hey everybody, I said I was going to do this a while ago, so I'm going to do it now, and I'm going to break this video into 3 separate parts because each part's probably going to be pretty long as it is, but I'm going to talk about what do we mean by size, specifically comparing things. What does it mean for something to be bigger than something else? And the 3 episodes will be what do we mean by bigger, and this first one is going to be how do we compare size. And these other 2 I think are relevant to the topic and show you how size can be interpreted differently or misinterpreted or used incorrectly, especially with this third one. I think this is going to be a good example of that. Now, one of the things you learn as a child, and young children can't discern very well, is how much of something do I have in something else, like how much water is in a glass. Now, if you give 2 glasses, I'm using graduated cylinders here because you can see the marks on them, they're plastic. If I was to give these to a small child who hasn't really grasped the concept of volume yet, and I show them these and ask them which one has more in it, which one has more stuff, they are going to point to this one. This is 25 milliliters, but so is this. It's just in a wider container, but it's the same amount of water in each cylinder. We like to think as we get older that we aren't fooled by such things as that, but if something is out of context, it can still trip us up as to what is meant by bigger, especially if someone like, I give you both of these and I say, okay, which one of these is bigger, guys? This one or this one? And that's all I say about it. You might go, this one is bigger. Well, yeah, it is volumetrically because, and this is going to come back as to key in this part and this part, so you'd say this one is bigger. And you would be correct if you were talking volumetrically. However, this has a lot more mass to it. There's a lot more stuff packed into the area of this rock. In other words, this has a higher density and this has a lower density. And I can put it on a scale to prove to myself, but the difference is large enough where I can feel it. And you know what? Let's do it. Let's take a weight of these, or mass, essentially, if you will. The 2 aren't the same, but we're going to treat them the same here. So first, we are going to weigh this rock here, 690.7 grams. Let's tear this out again. The ball, the sphere, is 100.8 grams. So our mass of this was about 690 grams. Almost 7 times more, 6.9 times more massive than this, which was almost right at 100 grams, which would explain the size that they picked for it, I guess. And the material, it's soft, it's spongy. You can hear it. And this I can't do that with. So when we're comparing apples to apples, like the amount of water in a container versus the amount of water in another container, we can pretty much answer, someone asks which is bigger, which has more, we can answer that because it's the same substance. But when you have something like those 2 objects there that are not the same density, it can trip you up a little. Now all of a sudden bigger can be volume or mass. Well, how do we know what to use? Okay, I need to talk about what do we mean by dimensions. I'm going to try to keep this simple. Now, basically a dimension can be from 0 to 1, 2, 3, 4, 5, etc., to infinity. But in physics, what is meant by a dimension is you take a single point and how many coordinates you need to find that point is essentially a dimension. And in our universe, we actually need 4 points. If I want to meet you anywhere on the planet, we want to meet up, there's 4 pieces of information I need. I need to know your latitude, your longitude, your elevation,
and a time to meet you. We are not going to deal with this fourth dimension. We are just going to deal with the three of space, all right? So what is meant by zero dimensions? Well, zero dimensions is a point. It's a single point. The entire universe is in a point, okay? And the only thing in this universe that may possibly have zero dimensions to it is a black hole, a singularity. I'm not talking about the event horizon. I'm talking about the actual black hole itself. That is suspected to have zero dimensions. So how do we create new dimensions? Well, we go basically 90 degrees to every existing dimension. So if you have zero, that's just a line. So one dimension is essentially a straight line. Okay? So any shape within a one-dimensional universe would just be a line segment. That's all it would be. Okay, so if we want two dimensions, we add 90 degrees to every existing dimension. So we only have the lines. We add 90 degrees, and we get basically a plane. All right, we would get a plane would be two dimensions. Now, if I took, say, a ball and slipped it through that second dimension, it would appear as a single point, so zero dimension, and it would slowly get bigger and appear as a circle until the ball started to pass through and the circle would shrink down to a point and then disappear. We call that basically a shadow. We basically, that's the shape it would appear to any two-dimensional creatures living on that plane. It would appear, a sphere would appear to be a circle that grows and then eventually shrinks. They have no concept of the third dimension, which would be 90 degrees to the plane, which is up, or a z-axis, if you will. And so we can think of that pretty comfortably when we talk about dimensions. Now we're going to get a little confusing. So what happens when we add 90 degrees to every angle in a cube? We get a hypercube, or a tesseract, it's also called. Just as a two-dimensional being cannot comprehend a sphere, we cannot comprehend a hypercube because we live in three dimensions of space. What we can picture is that tesseract moving through our universe, like the sphere moving through two dimensions would appear as a circle that grows and then shrinks to nothing. So we can picture what a hypercube looks like as a shadow, if you will, passing through our universe. But we can't picture four dimensions. I mean, just like if you take a cube and you unwrap it, make it 2D, it has 6 sides. Well, if you take a fourth dimensional hypercube and unwrap it, you get a structure with 8 cubes. So we can picture it that way. You can picture the unwrapped version of a hypercube, if you will. But to picture the actual hypercube, all we can do in our minds is look at the shadow. Now, mathematically, we can mathematically easily model a hypercube. Just like when you're figuring out area, you square things. When you're figuring out volume, you cube things. When you're figuring out the area of a hyper something, you take it to the 4th power.
So which is appropriate, mass or volume? It depends on the context. Now, mathematically, here are 2 ways you can calculate for either volume or mass. We're not going to run any calculations in this episode, so you're safe. We got more than enough in the next 2. So the volume is something that has planar sides to it in 3 dimensions, and we did this in our sandstone block episode. I can calculate the volume using length times width, my x and y, times height, my z. That's just one way. Obviously, the equation for the volume of a sphere is nothing like this. It's the basic principle is the same, because essentially in any volume calculation of a solid in 3 dimensions of space is going to involve length, width, and height. It just might be written bizarrely or some way you're not used to. And we're not going to talk about the sphere because we're going to beat spheres to death in the next one. Mass. Well, mass you can get directly from a scale like I did. Now, scales are meant to measure mass. And I need to say this. Things like grams, kilograms, ounces, pounds, these things are units of mass. Units of weight are expressed in newtons. When you go to the supermarket, no one buys 10 newtons of beef. Okay? We generally don't do things in weight. We do them by mass. And the scale I used got me grams, which is a mass. But is that accurate? Well, just so you know, I am in the northern hemisphere at about 41.5 degrees latitude. 45 degrees is the standard. The scale, although not perfect, is a really good approximation of mass on Earth at 45 degrees, either north or south latitude for all intensive purposes. And I think this confuses people. Like when you see the mass of the Earth, which we're going to talk about, you'll see it in kilograms, and it's a huge number. And the sun and planets. And then a lot of people will be like, how do you weigh the Earth? You're not weighing the Earth. You're getting a mass measurement. It's in kilograms when you see the mass of the Earth, okay? And the kilogram, although this might change in the next couple of years, the kilogram is the only metric unit still tied to a physical object. Everything else is no longer tied to a physical object. Even a meter isn't. Now, some people might be like, well, they use some elements and stuff like that, but they don't use those anymore. The meter is presently defined as a fraction of the speed of light. So generally, when we talk about size in 3 dimensions of space, we are either referring to mass or volume. And most scientists, like in chemistry and physics especially, when they are talking about size, they are talking about mass relationships, the mass of something to something else, which we'll get into here in the second episode. But in everyday speak, people may not be talking like that. Like, I'm pretty sure you've probably heard one of these following I'm going to write up on here, and this will pull us into our second episode a little bit. You may have read or heard that the sun is 100 times bigger than the Earth. I've seen this written in science news before, which, by the way, you should never get your actual science from the news. It's a good place to see what's hot, but don't get your science from news, okay? I don't care, even if they're a scientific magazine or newsletter, don't do it. There's legitimate sources to go to other than just magazines and blogs and things as such, although there could be good scientific information in those, but unless there's some sort of verification method, I suggest you go to get the information from the horse's mouth, okay? So I've seen this and heard this, and I've heard people spit this out before. The sun is 100 times bigger than the Earth. Okay, what does that mean? Well, if you ask a physicist or an astronomer, they're going to rip their hair out if they see something like this. Crap, I'm a geologist and I rip my hair out when I see this. This doesn't mean anything, all right? This is dealing with only one dimension of our 3-dimensional universe, and we'll talk more about that in the next episode. You may also have seen that the sun is 300,000 times larger than the Earth. And what do I mean by that? Well, first I just need to say that these are rounded. They're not questionable based on the rounding. They're questionable based on how they are defining bigger with no context. Well, 300,000 to 100, that's a huge difference. Oh, there's a third one you may have seen. You may also have seen this one. Wow. Those are really different. And there's another one that's not as common. That's about, I'm just going to write it there for you, about 12,000. All right? Times bigger. Well, crap. We know the sun is bigger than the earth. What's up with this? Well, I think we'll save that for the next episode here. But anyway, if you have any questions or comments, please leave them below, and I hope you learned something.